Hi everyone, in this video we saw problem 3.4 from the book Applied Thermodynamics, McConkey and Eastop. Here is the statement of the problem 4 from chapter 3. Steam at 7 bar, dryness fraction 0.9, expand reversibly at a constant pressures until the temperature is 200 centigrade. Calculate the work input and heat supplied per unit mass of steam during the process. Let me write the data that is provided in the statement. First is the pressure P1, Newton per meter square, multiply 7 with 10 to the power 5. Now it is in Newton per meter square. Initially the condition of the steam is 7 bar and dryness fraction. The steam means to say the first state point of the steam is in the wet region and its dryness fraction x1 is 0.9. The steam undergoes at a constant pressure, mean to say that pressure P1 must be same to pressure P2. The final state temperature is 200 centigrade, that is T2, it is 200, and also it says it is in the and also the second state of the steam is in the superheated region. Let me draw its PV diagram. This is the initial state of the steam. This is the final state of the steam. This is, let's say, initial state 1. This is the final state 2 of the steam, and the final state of the steam is in the superheated region, and its specific volume is V2 and the specific volume is V1, and the pressures of both at final state and the initial state is the same, and it is P1 is equal to P2 and it is 7 bar. Area under this curve represent the work done by the steam. During this process, heat is supplied to the steam. We need to calculate that. So what is our requirement? It is to find the work done by the steam, because here is expansion is taken place and the heat that is supplied during this process. Now come toward its solution. At initial state, the pressure P1 is 7 bar and dryness fraction x1 value is 0.9, that is given. If you see from the saturated steam table, let me show here the saturated steam table. Now I have taken the portion of the saturated water steam table. Here at 7 bar you can see the corresponding value of the specific volume, that is 0.2728 meter cube per kg. Here I can say that means to say Vg1 is equal to 0.2728 meter cube per kg, and the V1 value in this case is equal to x1 times of Vg1, that is 0.9 multiply 0.2728. So after its multiplications you will get the V1 value. Next is to find the enthalpy at state point 1. So the HF1 value, you can see this is HF1 value, that is 697 kilojoule per kg, and HFG1 value, that is 2067 kilojoule per kg, and the final enthalpy value and the initial enthalpy value at this state of the steam is H1 is equal to HF1 plus X1 HFG1. Now just simply put its value in this formula and you will get the initial enthalpy value at this state point. After solving this, you will get the enthalpy value H1, that is equal to 2557.3. Now the initial state point specific volume and enthalpy has been calculated with the help of this saturated water steam table. Now I will remove this from the screen because we have taken all the data that was our requirement at the initial state point, and also it covered a lot of workplace, so that's why I am removing it. P2, that is 7 bar, and temperatures T2, that is given 200 centigrade. And let me insert the superheated steam table portion on this display of screen so we can easily get its value. This is the portion of the superheated steam table. You can see from the 7 bar and temperature 200 centigrade, the corresponding specific volume value, that is V2, and it is 0.3001 meter cube per kg, and the final enthalpy at this point is H2 and it is 2846 kilojoule per kg. Okay, now the initial state and final state of the steam corresponding specific volume and enthalpy have been calculated. Next we need to calculate the work done by the steam, that is equal to pressures, change in volume, pressures and change in volume is V1 minus V2. What is pressure? That is 7 multiplied 10 to the power 5. What is V1 value? That is 0.2455. After solving this, you will get the work done by the steam, that is minus 38.2 kilojoule per kg. Next is to find the heat that is supplied during this process, that is equal to change in enthalpy, is equal to H2 minus H1. What is H2? That is 2846 kilojoule per kg. After simplifications, you will get the heat that is supplied is 288.7 kilojoule per kg. And this is our final answer. I hope you understand. If there is any confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed. Also share with your friends and colleagues for supporting me. Thank you so much.